the universe appears eternal. To the human eye, it seems stable and reliable. Stars remain in their places, galaxies rotate slowly, and the night sky changes little over thousands of years. This sense of permanence is deeply rooted in human culture and thinking. For most of history, the universe was perceived as an unchanging backdrop against which the brief drama of human life unfolds. For centuries, people believed the cosmos to be immutable. Civilizations rose and fell, empires collapsed, entire cultures disappeared, yet the stars remained. This created the illusion of eternity, the feeling that space itself existed beyond time and was not subject to the same laws as everything else. However, at the beginning of the 20th century, this idea was shattered. Modern science revealed that the universe is not static. It does not merely exist, it evolves, changes, and moves. This discovery became one of the most radical shifts in human understanding, because for the first time it suggested that everything that exists may have not only a beginning, but also an end. Cosmology, the science that studies the origin, structure, and fate of the universe, is based not on speculation, but on observation, physical laws, and mathematical models. When astronomers look deep into space, they are effectively looking into the past. Light from distant galaxies travels billions of years before reaching Earth. Every photon carries information about the state of the universe at the moment of its creation. These observations made it possible to determine that the universe was born approximately 13.8 billion years ago in an event known as the Big Bang. This was not an explosion in the conventional sense, but the beginning of the expansion of space itself. Time, matter, energy, and the laws of physics emerged simultaneously, defining the future evolution of the cosmos. In its earliest moments, the universe was extremely hot and dense. As it expanded, it cooled. Elementary particles formed atoms, atoms formed stars, stars gathered into galaxies, and galaxies assembled into vast cosmic structures. Space filled with light, energy, and motion. For a long time, it seemed that this process could continue forever. For decades, scientists believed that the expansion of the universe was gradually slowing down. This assumption appeared logical. The gravity of all matter should eventually slow the outward motion of galaxies. In this model, the universe resembled a stone thrown upward, losing speed until it eventually stops and begins to fall back. But at the end of the 20th century, astronomical observations led to an unexpected and unsettling discovery. By studying distant supernovae, scientists found that the expansion of the universe is not slowing down. It is accelerating. Galaxies are not merely moving away from one another, they are doing so at an ever-increasing rate. This discovery shocked the scientific community. It implied the existence of an unknown form of energy that counteracts gravity. This force became known as dark energy. Its nature remains one of the greatest mysteries of modern physics. Dark energy does not emit light and does not interact with matter in any familiar way. It reveals itself only through its influence on the structure of space. According to current estimates, dark energy makes up the majority of the universe's total content, far outweighing both ordinary matter and dark matter. With the discovery of dark energy, the question of the universe's future took on an entirely new meaning. If expansion is accelerating, the cosmos will become increasingly vast, cold, and empty. Galaxies will drift farther apart, stars will burn out, and complex structures will gradually disappear. At this point, the idea of the end of the universe ceased to be a philosophical abstraction. It became a scientific problem. Researchers began developing models that describe possible final scenarios, based on known physical laws and observational data. It became clear that the end of the universe may not be a single event, but a range of very different outcomes. Some scenarios predict a sudden and violent finale in which the very fabric of reality is destroyed. Others describe a slow fading, stretched across trillions or even quadrillions of years. In some models, the universe dies in catastrophe. In others, it simply loses energy and structure, sinking into eternal darkness. It is important to understand that none of these scenarios are predictions in the literal sense. They are not prophecies or fantasies. They are logical consequences of the physical laws known today. If these laws remain valid and unchanged, the universe is destined to follow one of these possible paths. The realization that the universe itself may be finite profoundly changes humanity's perspective on its own existence. Humanity becomes a fleeting episode in cosmic history, a brief moment between the birth and death of everything that exists. Yet it is precisely this moment that allows the universe to become aware of itself through conscious observers. The story of the end of the universe does not begin in the distant future. It begins here and now, at the moment humanity first understood that the cosmos is not eternal. This chapter marks the starting point of a documentary journey toward the final boundary of reality. Among all possible endings of the universe, one of the most disturbing is known as the Big Rip. This scenario describes a future in which the expansion of the universe becomes so violent that it ultimately destroys everything, from galaxies to atoms, and even the fabric of space itself. The foundation of the Big Rip lies in the mysterious force called dark energy. Discovered at the end of the 20th century, dark energy is responsible for the accelerating expansion of the universe. Unlike matter or radiation, it does not clump together. Instead, it pushes space apart, acting uniformly in all directions. In the standard cosmological model, dark energy behaves like a constant property of space itself. As the universe expands, more space is created, and with it, more dark energy. This leads to a subtle but relentless increase in its influence over cosmic evolution. The Big Rip scenario assumes a more extreme possibility, that dark energy is not constant, but grows stronger over time. In this case, the acceleration of the universe does not merely continue, it increases without limit. At first, the effects are barely noticeable. On the largest scales, galaxies continue to drift apart faster and faster. Galaxy clusters, once held together by gravity, begin to loosen. Distances that once could be bridged by gravitational attraction become too vast. As time passes, the expansion overwhelms gravity even within individual galaxies. Stars are torn from their orbits. Planetary systems lose stability. Planets no longer circle their stars in predictable paths, instead drifting away into an increasingly hostile cosmic environment. Closer to the final phase, the expansion reaches catastrophic levels. The force driving space apart becomes stronger than all known fundamental forces. Even objects bound by electromagnetic interactions, such as molecules and atoms, can no longer remain intact. Matter itself begins to disintegrate. Electrons separate from atomic nuclei. Protons and neutrons lose their structure. The very concept of a stable particle ceases to exist. Space is no longer a passive stage for events, it becomes the active agent of destruction. What makes the Big Rip particularly terrifying is its speed. Unlike slow scenarios that unfold over trillions of years, the final moments of the Big Rip occur rapidly. Once the critical threshold is reached, the remaining structures of the universe are destroyed in a fraction of a second. From a hypothetical observer's perspective, the end would be sudden and absolute. There would be no explosion, no shockwave, no final flash of light. Instead, reality itself would be stretched beyond the point where structure is possible. Space expands so violently that nothing can exist within it. Time, as a measurable quantity, also loses meaning. Without stable processes or particles, there are no clocks, no motion, no cause and effect. Physics, as it is currently understood, simply breaks down. Despite its dramatic nature, the Big Rip is not the most likely fate of the universe. Current observations suggest that dark energy behaves very much like a constant. However, uncertainties remain. The true nature of dark energy is still unknown, and even small deviations from current measurements could lead to radically different futures. For this reason, the Big Rip remains a powerful reminder of how limited human knowledge still is. It represents a universe destroyed not by collision or collapse, but by expansion itself, a paradoxical ending in which growth becomes fatal. In this scenario, there is no remnant left behind. No cold stars, no black holes, no lingering particles drifting through empty space. Everything that ever existed is erased, not by violence, but by excess. The Big Rip is the most extreme expression of cosmic acceleration, a future where the very force that drives the universe's expansion ultimately tears it apart. Yet if the universe avoids this fate, another ending awaits. One that is far quieter, far slower, and perhaps far more unsettling. Among all proposed scenarios for the end of the universe, the heat death is considered by many scientists to be the most probable. Unlike violent or sudden endings, this scenario describes a slow, inevitable fading of all activity, a future in which the universe does not collapse or tear itself apart, but gradually falls into silence. The concept of heat death is rooted in the second law of thermodynamics, one of the most fundamental principles of physics. This law states that in a closed system, entropy, a measure of disorder, always increases over time. As entropy rises, energy becomes more evenly distributed, and the ability to perform useful work diminishes. If the universe is indeed a closed system, then its long-term fate is governed by this law. Over immense spans of time, all differences in temperature, pressure, and energy must eventually disappear. When equilibrium is reached, no physical process capable of producing change can continue. At present, the universe is far from this state. Stars burn brightly, galaxies collide, and energy flows from hot regions to cold ones. These differences power all cosmic activity, but they are finite. Every star is a machine fueled by nuclear reactions, and like all machines, it will eventually stop. Stars shine by converting hydrogen into heavier elements through nuclear fusion. This process releases enormous amounts of energy, allowing stars to emit light and heat for billions of years. However, the fuel supply is limited. Once hydrogen is exhausted, stars begin to die. In the distant future, star formation will come to an end. The interstellar gas clouds from which stars are born will be depleted or locked away in stellar remnants. Without new stars, the universe will gradually grow darker. Galaxies will become collections of dead stars, white dwarfs, neutron stars, and black holes. Over time, even these remnants will cool. White dwarfs will fade into black dwarfs, emitting almost no radiation. Neutron stars will lose their residual heat. Motion will slow, and structure will weaken. Black holes, often thought of as eternal, are not exempt from this fate. According to quantum theory, black holes emit an extremely faint form of radiation, known as Hawking radiation. Over unimaginably long timescales, far longer than the current age of the universe, black holes will gradually lose mass and evaporate completely. As the last black holes disappear, the universe will enter a state dominated by low-energy particles and radiation. Matter will be sparse, widely separated, and incapable of forming complex structures. Temperatures everywhere will approach absolute zero. At this stage, time itself becomes difficult to define. Time is measured through change, through processes, motion, and interaction. In a universe where nothing changes, the distinction between past, present, and future loses its meaning. This is the essence of heat death, not destruction, but final equilibrium. The universe reaches a state in which entropy is maximized and no further evolution is possible. There are no explosions, no dramatic finales, no final moments of chaos. Instead, there is endless stillness. What makes this scenario particularly unsettling is its inevitability. If the laws of thermodynamics remain valid, and if dark energy continues to drive expansion at a steady rate, the heat death appears unavoidable. It is not a catastrophe that can be delayed or prevented, only postponed by immense spans of time. In this future, life cannot exist. All biological processes depend on energy gradients, on differences between hot and cold, order and disorder. Without such differences, chemistry itself becomes inert. The universe becomes hostile not through violence, but through indifference. Some theories suggest that rare quantum fluctuations could still occur even in this frozen cosmos. Over infinite time, improbable events might happen. But such possibilities remain highly speculative and offer little comfort in the face of an otherwise lifeless eternity. The heat death represents the ultimate consequence of expansion and entropy. The universe does not end with a scream, but with a whisper, a gradual fading into darkness and silence. If this scenario is correct, then the end of the universe will not be an event that happens at a specific moment. It will be a condition, a final state that, once reached, persists forever. Yet not all models agree that this is the only possible fate. Other scenarios propose a very different ending, one in which expansion is reversed and the universe collapses back into itself. That possibility leads to another vision of the end. Before the discovery of dark energy, many scientists believed that the ultimate fate of the universe would be determined by gravity. If the total amount of matter and energy were great enough, gravitational attraction would eventually slow the cosmic expansion, bring it to a halt, and then reverse it. This scenario became known as the Big Crunch. In this model, the universe is not destined to expand forever. Instead, it behaves like a massive cosmic breath, expansion followed by contraction. After reaching a maximum size, space itself begins to shrink, pulling galaxies, stars, and all matter back toward a final collapse. As expansion slows, the distances between galaxies decrease. Clusters that were once moving apart begin drifting back toward one another. Collisions between galaxies become increasingly common, reshaping their structures and triggering intense bursts of star formation. As contraction accelerates, the universe grows hotter and denser. Background radiation increases in temperature. Matter becomes more tightly packed, and energy levels rise dramatically. The large-scale structure of the cosmos begins to break down as everything is drawn inward. In the later stages of the Big Crunch, conditions start to resemble those of the early universe. Temperatures soar to extreme levels, and densities approach values last seen shortly after the Big Bang. The distinction between individual objects becomes meaningless as matter and energy merge into a single, highly compressed state. Stars no longer exist as separate entities. Atoms are crushed. Even atomic nuclei are forced together under overwhelming pressure. The universe becomes a seething, opaque plasma where the known laws of physics begin to lose their predictive power. One of the most intriguing aspects of the Big Crunch is its possible connection to the beginning of the universe. Some theories suggest that the final collapse could trigger a new expansion event, another Big Bang. In this interpretation, the universe is cyclic, endlessly repeating a sequence of birth, evolution, collapse, and rebirth. Such cyclic models offer an appealing symmetry, a universe without a true beginning or end, only transitions. Each cosmic death becomes the seed of a new creation. However, this idea remains highly speculative. Modern observations present a serious challenge to the Big Crunch scenario. Measurements of distant supernovae, cosmic microwave background radiation, and large-scale structure all indicate that the expansion of the universe is accelerating, not slowing down. This suggests that gravity alone is insufficient to reverse expansion. If dark energy continues to dominate cosmic evolution, the Big Crunch becomes increasingly unlikely. To occur, dark energy would need to weaken, vanish, or change its behavior entirely, possibilities that remain hypothetical. Nevertheless, the Big Crunch remains an important concept in cosmology. It represents a universe destroyed not by dispersion, but by collapse. Instead of fading into emptiness, everything that exists is drawn together into a final, catastrophic convergence. From a philosophical perspective, the Big Crunch is a dramatic mirror of the Big Bang. Where the universe once expanded from an infinitesimal point, it now returns to one. Time, space, and matter converge toward a final singularity. What happens at that singularity is unknown. Current physical theories cannot describe conditions of infinite density and temperature. Whether time itself would end, reverse, or give rise to a new beginning remains an open question. The Big Crunch may no longer be the favored model, but it continues to play a vital role in understanding cosmic possibilities. It reminds us that the fate of the universe depends not only on what exists within it, but on how the fundamental forces evolve over time. If the universe does not collapse, and if it does not tear itself apart, other endings remain. Some are sudden and unpredictable, driven not by gravity or expansion, but by the fragile nature of reality itself. One of these possibilities lies hidden in the quantum structure of space. Among the most startling and unpredictable scenarios for the end of the universe is vacuum decay. This possibility emerges from the strange and counterintuitive world of quantum physics, where even empty space, the vacuum, is not truly empty, but a seething field of potential and instability. In classical physics, a vacuum is defined as a space devoid of matter. Yet quantum mechanics tells a different story. Even in the absence of particles, the vacuum contains fluctuating energy fields. These fluctuations give rise to ephemeral particles that appear and disappear within fractions of a second. In this dynamic landscape, the vacuum itself can exist in different states, each with its own energy level and stability. Current understanding suggests that the vacuum of our universe might not be in the lowest possible energy state. In other words, it could be metastable, stable enough to persist for billions of years, but ultimately susceptible to a sudden transition to a more stable state. This transition is known as vacuum decay. If such a decay occurs, it would begin at a single point in space, creating a bubble of true vacuum, a region where the fundamental laws of physics differ from those in our familiar universe. This bubble would expand at nearly the speed of light, consuming everything in its path. The very constants of nature, the forces that govern atomic bonds, nuclear stability, and chemistry, would be altered inside the bubble. For any observer, the effects would be instantaneous. Atoms would disintegrate. Molecules would break apart. Stars and planets would cease to exist. Light itself might no longer behave as it does now. In the blink of an eye, reality would be transformed, leaving behind a universe unrecognizable to any current understanding. Unlike other cosmic finales, vacuum decay offers no warning. No signals travel faster than light, and the expansion of the true vacuum occurs at nearly light speed. Humanity, or any intelligent life, would have no time to react. The end would arrive silently and without forewarning. The idea of vacuum decay stems from quantum field theory and the possibility that the Higgs field, the field responsible for giving particles their mass, might be in a metastable state. While current measurements of the Higgs boson and other particles suggest our vacuum is likely long-lived, the possibility of instability cannot be entirely ruled out. Vacuum decay represents a universe destroyed not by heat, gravity, or expansion, but by the intrinsic instability of existence itself. It is a reminder that the cosmos is governed by fundamental principles that are beyond direct control or influence. Some theoretical physicists have speculated about the consequences of such an event. In a vacuum bubble, the very rules of causality and quantum mechanics could change. Matter as we know it would no longer exist. Energy might be redistributed in ways impossible to predict. The observable universe could be reduced to a new vacuum state, devoid of structure, complexity, or life. The terror of this scenario lies in its inevitability once triggered. Unlike the Big Rip or the Big Crunch, which require specific cosmic conditions over vast timescales, vacuum decay can happen instantaneously and irreversibly. It is not a gradual fading of light or slow collapse. It is a complete rewriting of reality. In contemplating vacuum decay, one confronts the fragility of existence at its most fundamental level. Even in a universe that appears stable, the underlying quantum structure may harbor seeds of sudden and absolute annihilation. Yet, despite its unsettling nature, vacuum decay is largely theoretical. The probability is extremely low within the current age of the universe, and the precise behavior of the Higgs field and other quantum phenomena remains under investigation. Nevertheless, it stands as one of the most extreme illustrations of cosmic impermanence. In this scenario, the universe does not end with sound, spectacle, or a visible explosion. It ends as a quantum inevitability, a silent transformation from one state of reality to another, leaving only a void in its wake. And even if vacuum decay does not occur, the universe still faces other profound endings. Some involve the slow disappearance of matter, some the final evaporation of black holes, and some even the ultimate change of the laws of physics themselves. In the distant future, after the stars have burned out and galaxies have drifted apart, the universe will enter a stage dominated by one of its most enigmatic and powerful objects, black holes. These regions of space, where gravity is so intense that not even light can escape, are the ultimate survivors of cosmic evolution, remnants of dead stars, collapsed matter, and collapsed galaxies. Black holes are often considered eternal. For billions or even trillions of years, they continue to exist, absorbing matter and radiation that stray too close. In a universe where all other sources of energy have vanished, black holes become the last reservoirs of mass and gravitational influence. They are silent sentinels in an ever-cooling cosmos. Yet black holes are not truly immortal. In 1974, Stephen Hawking proposed the groundbreaking idea, Hawking radiation. According to quantum mechanics, black holes are not entirely black. Particle-antiparticle pairs constantly form near the event horizon, and occasionally, one particle escapes, appearing as radiation. This process causes the black hole to slowly lose mass. Hawking radiation is incredibly weak. For stellar-mass black holes, evaporation occurs over timescales vastly exceeding the current age of the universe, many orders of magnitude beyond 13.8 billion years. Supermassive black holes, the giants residing in the centers of galaxies, will take even longer, their lifespans stretching toward 10^1 years or more. As black holes gradually evaporate, the matter they once contained is transformed into low-energy radiation, dispersed across an ever-expanding space. This radiation is faint, diluted, and incapable of forming new structures. Over unimaginable durations, the universe becomes a vast, near-empty expanse of photons, neutrinos, and other subatomic particles. The disappearance of black holes marks the final act in the story of matter. Where once there were stars, planets, and galaxies, only diffuse radiation and elementary particles remain. The cosmos has lost not only its structures but also the sources of observable energy that make measurement, observation, and life possible. This stage is the final expression of cosmic entropy. The universe has reached a point where the building blocks of matter themselves are nearly gone. Stable particles, such as protons and electrons, may still exist, but their interactions are infrequent and largely insignificant. The complex structures that once defined the universe, atoms, molecules, stars, planets, have vanished. In this era, the universe is incredibly cold. Temperatures approach absolute zero. Motion is minimal. Time, measured through change, becomes almost meaningless. Processes that once marked the passage of epochs, stellar fusion, planetary orbits, chemical reactions, no longer occur. The cosmos drifts toward an ultimate quiet. Some theoretical physicists speculate about the fate of even elementary particles. Protons may decay over extremely long timescales, leading to a universe where even the fundamental constituents of matter disappear. If this occurs, matter as we know it ceases entirely, leaving a universe composed almost entirely of radiation and vacuum energy. The disappearance of matter through black hole evaporation is not dramatic in a visual sense. There are no cataclysms or fireworks. Instead, it is a gradual dissolution, a slow unweaving of the material universe into a cold, dark, and nearly empty expanse. Black holes, once feared for their destructive power, thus play a paradoxical role. They are both the last bastions of cosmic matter and the agents of its final dispersal. Through Hawking radiation, even these titanic objects eventually return their contents to the void. This scenario emphasizes the transient nature of all things. From the first stars to the last black holes, nothing persists forever. Even the strongest gravitational wells succumb to the inexorable laws of physics. And yet, even after all matter has disappeared, the universe is not entirely inert. Space, time, and energy still exist, though in forms that are profoundly altered. The cosmos may remain a quiet, diffuse sea of low-energy radiation for trillions upon trillions of years, stretching into the unimaginable depths of time. In this stage, observers, if any could survive, would find a universe almost unrecognizable. No structure, no light, no warmth. Only the faint whispers of remnants drifting through the eternal darkness. Even after black holes vanish, other cosmic possibilities linger. Some involve changes in the fundamental laws of physics themselves, others envision entirely new cycles of cosmic birth and death. The story of the universe's end is not merely about destruction, but about the transformation of reality itself. In the vast timescales of the universe, even the fundamental rules that govern reality may not remain constant. The possibility that the laws of physics themselves could change presents one of the most profound and unsettling scenarios for the end of the cosmos. While less tangible than the dissolution of matter or the expansion of space, such changes could render existence as we know it impossible. Physics, at its core, relies on constants, quantities that define the strength of forces, the masses of particles, and the properties of space and time. Constants such as the speed of light, Planck's constant, and the gravitational constant provide the framework for everything from the motion of planets to the formation of atoms. Our understanding of chemistry, biology, and cosmology depends on the stability of these values. Yet, some theoretical models suggest that these constants may not be immutable. In certain conditions, subtle variations could occur over astronomical timescales. Even a tiny change in one constant could cascade into dramatic effects, fundamentally altering the structure of the universe. Consider the delicate balance of forces that holds matter together. Atomic nuclei exist because the strong nuclear force counteracts electromagnetic repulsion between protons. If the strength of this force were slightly weaker or stronger, atoms might not form at all, or they could collapse instantly. Molecules, the building blocks of chemistry, would cease to exist. Stars would never ignite, or they might explode unpredictably. Changes in the speed of light or the gravitational constant could have equally profound consequences. Galaxies might tear themselves apart or collapse uncontrollably. Planetary systems could destabilize, and time itself, as measured by physical processes, might behave differently. Space would become alien, unrecognizable to any observer accustomed to familiar physical laws. One speculative scenario involves a spontaneous phase transition of the vacuum, related to the previous chapter on vacuum decay. In this case, the energy underlying the universe shifts to a new configuration, altering all constants simultaneously. Matter, energy, and even space-time itself could be redefined, leaving the universe in a state incompatible with current physics. The implications extend beyond matter. Forces such as electromagnetism and gravity might no longer operate in predictable ways. Radiation could propagate differently or not at all. The universe would no longer support complex structures or processes. Life, as well as stars, planets, and galaxies, would become impossible. Unlike the gradual processes of heat death or black hole evaporation, changes in fundamental laws could occur suddenly and globally. There would be no intermediate stage, no opportunity for adaptation. The universe would continue to exist, but in a form completely alien to any observer grounded in the physics we know. This scenario underscores the fragility of reality itself. While stars and galaxies are temporary, and black holes eventually evaporate, the laws of physics appear eternal, until they are not. If these constants shift, the universe could survive in name only, reduced to a strange and unknowable state devoid of structure or coherence. Cosmologists debate whether such changes are likely or even possible. Observations of the cosmic microwave background, atomic spectra in distant galaxies, and other astrophysical measurements suggest remarkable stability over billions of years. Yet the universe's future spans timescales far beyond these observations. Over trillions, quadrillions, or even googolls of years, even the constants may falter. In confronting this possibility, humanity faces a cosmic perspective unlike any other. The end of the universe may not involve heat, expansion, or collapse. It could involve the transformation of reality itself, the rewriting of the rules that define what is possible. Changes in the laws of physics, if they occur, represent a universe in which survival is meaningless, observation impossible, and continuity of cause and effect obliterated. It is a stark reminder that the cosmos is not a permanent or predictable stage, but a dynamic system capable of profound transformation. Even if such changes never occur, other endings remain. The universe might drift into quiet entropy, dissolve through vacuum decay, or undergo cycles of death and rebirth. Each scenario is a testament to the richness, complexity, and ultimate impermanence of reality. Among the most intriguing possibilities for the fate of the universe is the idea of a cyclical cosmos, in which endings are not final, but transitions. In this model, The death of one universe becomes the seed for the birth of another, creating an eternal cycle of expansion, contraction, and renewal. The concept of a cyclical universe is ancient in human thought. Philosophers and mystics imagined worlds that rise, fall, and rise again, a rhythm mirrored in natural cycles on Earth, from the changing seasons to the patterns of life and death. Modern cosmology has adapted these ideas, exploring whether the universe itself might follow a similar pattern on incomprehensibly vast timescales. One version of the cyclical model envisions a series of big bangs and big crunches. After expanding and evolving, the universe might eventually collapse under gravity, forming a singularity akin to the initial state of the Big Bang. Then, from this singularity, a new expansion begins, birthing a new cosmos with new stars, galaxies, and possibly new forms of life. In this view, the end of one universe is merely a pause before the next creation. Another variant incorporates dark energy and cosmic acceleration. Some theories suggest that even in an eternally expanding universe, subtle quantum fluctuations or changes in the vacuum state could trigger a collapse or a new phase of cosmic inflation, effectively restarting the cycle. Unlike the finite deaths of other scenarios, this model offers a kind of cosmic immortality, with no ultimate finality. The appeal of cyclical models lies in their symmetry. They offer a framework in which creation and destruction are intimately linked, each leading naturally to the other. The universe becomes less a linear story with a definitive beginning and end, and more a cosmic heartbeat, an ongoing oscillation beyond the comprehension of human lifespans. However, these models face significant challenges. Observations of the accelerating expansion, driven by dark energy, suggest that a complete contraction may be unlikely under current conditions. If the repulsive effect of dark energy continues indefinitely, the universe may expand forever, preventing the collapse necessary for a new cycle. Even so, theoretical physicists continue to explore mechanisms that could allow cycles to occur. Some involve modifications of general relativity, the influence of extra dimensions, or the dynamics of quantum fields in extreme conditions. While speculative, these ideas push the boundaries of our understanding, reminding us that the universe may harbor possibilities beyond what is currently observable. The cyclical universe also raises profound philosophical questions. If the cosmos undergoes repeated cycles, what happens to information, structure, and memory? Are remnants of previous universes carried forward, or is each cycle a fresh slate? Could life, in some form, recur endlessly? Such questions remain open, blending physics with metaphysics in a way unique to cosmology. From a human perspective, the cyclical model reframes the idea of cosmic mortality. Instead of a finite story culminating in emptiness, the universe becomes a continuing saga, a rhythm of creation and dissolution that stretches into the infinite. Death is temporary, endings are preludes to new beginnings. Yet even in cyclical models, individual universes, including our own, have lifespans. Stars will burn out, galaxies will drift apart, and black holes will evaporate before the next cycle begins. The scale of existence remains vast, but finite from the perspective of a single cycle. In contemplating a cyclical cosmos, humanity gains a different understanding of impermanence. Even as one universe fades into darkness or collapses into a singularity, another awaits, emerging from the same laws of physics that govern our current reality. This vision offers a form of cosmic hope, that existence is not doomed to absolute finality, but part of a rhythm that transcends individual epochs. Ultimately, the cyclical universe challenges our perception of time and ending. It suggests that the story of the cosmos is neither linear nor final, but eternal in its progression, with death and birth inseparably intertwined. Beyond all scenarios of cosmic collapse, expansion, or transformation lies a profound and unsettling possibility: the end of time itself. Time, as we understand it, is a measure of change, a sequence of events, a flowing continuum in which cause precedes effect. But what if, in the far future, all change ceases? What if the universe reaches a state where time no longer has meaning? In the earliest moments of the cosmos, time began as part of the Big Bang. Space and time are intertwined in the fabric of reality, forming a four-dimensional continuum described by general relativity. Clocks tick because processes occur. Motion is measured because matter moves. Events happen in succession, creating the arrow of time that guides the evolution of the universe. Yet the arrow of time depends on processes and differences, temperature gradients, energy flows, the motion of particles. Without these, time cannot be measured. A universe in perfect equilibrium, with no energy gradients and no physical activity, is effectively timeless. There is no past, no present, no future, only a static existence. Scenarios like heat-death illustrate this concept. As stars burn out and black holes evaporate, energy spreads evenly across space. Gradually, all thermodynamic processes cease. Entropy reaches its maximum, and the universe reaches a state of cosmic stasis. In such a world, clocks no longer tick, events no longer occur, and the familiar passage of time becomes meaningless. Even more extreme scenarios, such as the disappearance of matter through black hole evaporation or changes in the laws of physics, reinforce this outcome. Without particles, forces, or interactions, there is no medium to carry information or sustain events. Time, in effect, becomes an empty concept, a label applied to nothing. The philosophical implications are staggering. If time ends, then the universe exists in a frozen present, an eternal snapshot of reality. Change is impossible, observation meaningless. Past and future lose all distinction. For any hypothetical observer, or consciousness, existence is reduced to a timeless void. Some cosmologists argue that quantum fluctuations might still occur, introducing minimal change even in a universe dominated by stasis. But such events are rare, probabilistic, and over immense scales, largely insignificant. The universe would still appear frozen, an infinite expanse of unchanging nothingness. The end of time also challenges our understanding of causality. Cause and effect require sequential events. Without time, sequences dissolve. There is no before and no after. In this final state, the universe is not destroyed in the conventional sense. It does not collapse or explode. It simply ceases to evolve, slipping into a silent, eternal equilibrium. Humanity, in contemplating this scenario, confronts the ultimate cosmic perspective. All that we know, all that we measure, depends on the progression of time. Without it, knowledge, memory, and observation are impossible. The universe remains, but its story is complete. The narrative ends with the cessation of change. Yet, even in this silent eternity, the laws of physics and the structure of space remain as a framework. Space exists, but it is uninhabitable, inert, and frozen. Energy is present, but inaccessible. The universe is a stage with no actors, a cosmos with no events, a reality in which time itself is gone. The end of time may seem abstract, almost philosophical, yet it is a scientifically grounded possibility. It is the logical conclusion of entropy, energy depletion, and cosmic expansion. It is not violent, not sudden, not dramatic. It is the quietest of all endings, the fading of existence into a state beyond measurement, beyond observation, beyond becoming. In this scenario, the universe exists in permanence, yet it is meaningless in terms of change or activity. Past, present, and future converge into a singular, eternal now. Time has ended, and with it, the story of cosmic evolution reaches its final chapter. Even after time ends, some possibilities linger in theory: changes in laws, quantum fluctuations, or cyclical rebirths. The universe may not simply vanish, it may transform, restart, or persist in ways beyond human comprehension. Yet, in the absence of time, our familiar concept of existence is irrevocably lost. The end of the universe is not a tragedy in the human sense. It is the inevitable consequence of natural laws, a silent conclusion to a story that began nearly 14 billion years ago. In this cosmic narrative, humanity, and any observer, exists only for a fleeting instant, a brief consciousness amidst the vast expanse of space and time. Yet even in this ephemeral role, humans bear witness to the unfolding of reality itself. Throughout its history, the universe has evolved in ways both magnificent and terrifying. Stars ignited and died, galaxies collided and merged, black holes consumed light and matter, and the invisible forces of dark energy stretched the fabric of space. Each stage of cosmic evolution, from the first moments after the Big Bang to the cold, lonely stretches of the far future, is a testament to the inexorable power of physical law. For humans, observation is not merely passive. By studying the stars, by measuring cosmic radiation, by developing mathematics and physics, we become participants in the universe's story. Our knowledge transforms mere existence into meaning, however temporary. We understand that the universe is vast, ancient, and impermanent, and in understanding, we bear witness to its fleeting grandeur. As cosmic endings approach, whether through the violent tearing of the Big Rip, the slow fading of heat death, the collapse of the Big Crunch, the sudden rewrite of vacuum decay, or the dissolution of matter itself, the role of the observer becomes even more poignant. To witness these possibilities, even in theory, is to confront the fragility of reality. Every structure, every process, every form of matter, and even time itself, is impermanent. Yet the universe does not end because of tragedy or failure. It ends because of laws that have guided its evolution from the first instant. Gravity, electromagnetism, quantum mechanics, and thermodynamics are impartial arbiters. They do not grieve, rejoice, or notice. They act consistently, impartially, and inevitably. The end is not personal, it is inevitable. Even in the most extreme scenarios, such as vacuum decay or the cessation of time, the universe's conclusion is not dramatic in spectacle. There is no final flare visible to any eye, no crescendo of destruction, no cosmic scream. It is a quiet event, a transformation or cessation of processes. And yet, for the witness, the human mind capable of reflection, the enormity is staggering. The idea of being the last witness highlights a profound truth. Consciousness is transient, yet perception matters. Humanity, and any sentient observer, will experience only a minuscule fraction of cosmic history. Yet in that fraction, the universe gains an observer, a consciousness that reflects upon itself. In this brief span, the cosmos achieves a kind of awareness, however fleeting. In contemplating the universe's end, humans confront questions that are both scientific and existential. What is the meaning of time in a timeless cosmos? What is the significance of matter when all matter will vanish? How can life find purpose in a universe destined for silence? These questions are not answerable in a final sense, yet the act of asking them, of observing, reasoning, and bearing witness, is itself a form of significance. The final act of the universe, in every scenario, is its transformation or cessation. Space may expand until it is nearly empty, matter may disintegrate into radiation, black holes may evaporate, fundamental laws may shift, and time may cease. But even as these processes unfold, the universe remains a story, witnessed at least once, by life capable of reflection. Humanity is both insignificant and crucial. Insignificant, because our presence is but a fleeting moment. Crucial, because we are the universe's way of knowing itself. The stars, galaxies, black holes, and dark energy will continue their trajectories regardless of our existence. Yet our observation, our understanding, is the last imprint of awareness on the cosmos. The universe's ending, therefore, is both absolute and intimate. It is absolute, in the sense that natural laws are impartial and inevitable. It is intimate, in the sense that consciousness, however transient, allows the cosmos to witness its own grandeur, complexity, and finality. In the act of observing, humanity becomes the last witness, the final chronicler of existence. In this final chapter, the universe does not end with chaos, fury, or spectacle. It ends as it has always existed, as a governed, law-bound reality, evolving according to the principles that gave rise to stars, life, and thought. And in the brief flash of human consciousness, it achieves something extraordinary, the awareness of its own existence, and the silent acknowledgement of its eventual conclusion. The story of the universe, from birth to the ultimate end, is a tale of transformation, evolution, and inevitability. And though the cosmos itself may vanish, be rewritten, or fade into stillness, its memory persists, carried, for a fleeting moment, in the mind of its last witness.